what you're looking at here is part of a sheet that's posted in D2L with these identities on it. In fact, we looked at the first part of it with cosine on it previously. This is the latter part of it. And all of these identities are those which are covered in section 4.3. And we'll focus on these for this video. Now, of course, I want to point out some of the helpful tricks with these identities just to help us remember them. If we take a first look at the sum of angles for sines, notice a couple things. First of all, the sine in between A and B actually matches the sine in between the terms on the right side in both cases. So sine of A plus B has a plus in it. The sine of A minus B has a minus in it. Furthermore, the order of the sines and cosines on the right side are switched around. So here's the way I like to remember it. So sine starts with S, and so does the word surround. And so in these formulas, the sines surround on the right side expressions in both cases on the outside. So the sines are surrounding the cosines. Okay, so the sine sum of angle identities has the same sign in the middle, and the sine surrounds the cosines. Alright, those can help us remember these. Let's move on to tangent. Now the tangents are just, they look a little more complicated, but they're not bad. Notice a couple things. The sign in between the A and the B, so tangent of A plus B, that sign matches the one in the numerator, tan A plus tan B. Same thing below for sine of A minus B. The numerator there is tan A minus tan B. So those signs match. Good to know. And then the signs that are in the denominators of each are the opposites. So we had a plus above, it's a minus below, minus above, it's a plus below. So those little tricks can just help memorizing them. Again, you might have to write them out by hand several times a week just to keep them fresh in memory, since you'll have to know them for tests. Now let's move on to the bottom where we have these co-function identities. Now I just want to explain these for a brief moment. Co-functions are things we've been dealing with already, such as sine and cosine. That's right, they do go together, and these identities kind of tie them in a meaningful way. What they mean is this. If you look at each of these inputs, we have pi over 2 minus x, pi over 2 minus x, pi over 2 minus x. And by the way, remember, pi over 2 is the same thing as 90 degrees, so it doesn't actually matter which you use, degrees or radians, but they are synonymous. What this means then in each case is that these angles, pi over 2 minus x and x, notice those occur each time, pi over 2 minus x and x, those are called complementary. Complementary angles add to 90 degrees. So, for example, 60 plus 30 add to 90 degrees, so 60 degrees and 30 degrees would be complementary. What these co-function identities basically say, I think, is a little easier to remember in words. And here's what it is. Co-functions of complementary angles or arcs, okay, so co-functions of complementary angles are equal. Now you can go ahead and check this little sentence here by testing an example. Take some complementary angles that I gave a moment ago, such as 60 and 30. What is the cosine of 60? 60 degrees, of course. The cosine of 60 degrees should be 1/2. Okay, now what is the sine of its complement? So the sine of 30 would also be 1/2. So that's an example of this phrase. Co-functions of complementary angles are equal. Let's take a look at an example where we might be able to apply our identities and try to find the tangent of 13 pi over 12. Now we've seen this trick before. 13 pi over 12 is not one of our unit circle values, so we're going to have to split it up into arcs or angles that are on our unit circle. So let's see if we can find a convenient way to do that. The tangent of 13 pi over 12 should turn out to be the same as the tangent of 9 pi over 12 plus well, what would the second one be if I have to add these to 13 pi over 12? Yeah, it'd have to be 4 pi over 12. And then let's reduce each of those fractions to see where that leaves us. That would mean we have the tangent of 9 pi over 12 is really 3 pi over 4. And 4 pi over 12 is really pi over 3. And those, of course, are some nice unit circle values for us. So now let's go ahead and evaluate these, with the first of these being what we'll call A, and the second pi over 3 here being our B. And we're going to use our sum of angle identity for tangent to set these up. So let's go ahead and do that. We'll say that this is equal to the tangent of A, which of course is 3 pi over 4, plus the tangent of B, which is our pi over 3. That's our numerator. And then the denominator, and notice, by the way, the same sign occurs, right? This is sine of angle A plus angle B. The plus matches the numerator. In the denominator, we have the opposite sign, though. We have 1 and then minus tangent of A, or in other words, tangent of 3 pi over 4, times the tangent of B, which is pi over 3. Now all we have to do is turn these into some nice unit circle exact values and we'll be good to go. So the tangent of 3 pi over 4 should be negative 1. So that replaces this first tangent. Now we'll add the second expression, tangent of pi over 3. This is root 3. Okay, that's replacing that second numerator value. Then down below in the denominator we have 1 minus really the same values we've already used. The tangent of 3 pi over 4 would be negative 1, and the tangent of pi over 3 would be root 3. We can simplify this a little bit if we just rewrite this as, I'm going to go positive first here to make this root 3 minus 1 in the numerator. I haven't changed anything, I just switched the order of those two terms. And then in the denominator I can simplify the negative to make this 1 plus root 3. Now that looks better, but it's still not quite good. In fact, we would always like to try to rationalize things if we can, and as you might recall, a denominator like this with a root in it can and should be rationalized. So now I've just rewritten our expression here, but I want to rationalize it, and as you might recall, to rationalize when you have two terms in a denominator, one of them being a root, we have to multiply by what's called the conjugate. It's basically the same thing with the opposite sign. So I'm going to multiply by root 3 minus 1, but then of course I have to do the same thing to the numerator. So this will be root 3 minus 1 above also. And let's go ahead and multiply all this stuff together to see where this goes. We can FOIL things together in the numerator. Root 3 times root 3 is 3. Outer times outer and inner times inner are the same. Those will give us minus 2 root 3. And then last times last would be plus 1. So that's the numerator getting FOILed together. The denominator you could FOIL also. Of course, the shortcut of this is that this is just a difference of two squares. That's exactly what conjugates are meant to be. So first times first, of course, will be 3. The inners and outers will always cancel with conjugates, so you can just skip right to the last times last, which would be a minus 1. Alright, now let's see if we can get this any simpler. If you look at the numerator, we can combine the 3 plus the 1 to get 4 minus 2 root 3. And then in the denominator, 3 minus 1, of course, is 2. And then we can simplify each of these by factoring out a 2 from the numerator to give us 2 minus root 3. That's still all over 2, but now after factoring, those 2's could cancel. And so we're left with the final result of 2 minus root 3. Let's take a look at one more example where we want to prove or show the following identity. We want to prove that the cosine of a minus b over the cosine of a sine of b is equal to the tangent of a plus the cotangent of b. Now, remember our strategy, which is start with the more complicated looking side. I hope it's clear that the left side of this original equation looks more complicated. So I'm going to rewrite that and then see what we can do with it. We have the cosine of a minus b over the cosine of A times the sine of B. Now the thing that should be jumping out at us is the numerator of this fraction, which is a difference of angles cosine identity. So let's go ahead and just rewrite that using that identity to get going here. The cosine of A minus B, according to our identities, is the same as the cosine of A times the cosine of B. And then remember, we use the opposite sign, so we had a difference in between here on the left side, which means we use a plus on the right side, and then we put our signs, so sine of A, sine of B. Now let's drag our denominator over and just leave it as is for now, which was cosine of A, sine of B. Alright, now you might recall one strategy from all these prove or show problems, which is typically we want to combine fractions by getting a common denominator and adjusting accordingly and going from there. Well, ironically enough, it's also a strategy to split up fractions. What we're looking at now on the right side is really already combined. We want to go the other way and split it up. So we're going to take the two different terms we have in the numerator and rewrite each of them over their own version of this common denominator. So this will give us cosine of A, cosine of B over the denominator here, which is cosine of A, sine of B, plus, now onto the right term in the numerator, that'll be sine of A, sine of B, over the same denominator here, cosine of A, sine of B. So we've successfully split up these fractions, but now we have to reduce them a little bit. Notice though, in the first fraction, there's a cosine of A over a cosine of A. Those would cancel right out. And in the second fraction, there's a sine of B over a sine of B, and those would cancel right out. What's left would be a cosine of B over a sine of B plus sine of A over cosine of A. Now let's use our trig identities here. The cosine of B over the sine of B is really the same thing as cotangent of B. And moving on, the sine of A over the cosine of A is really the same thing as the tangent of A. Now take a look at where we wanted to go. We started on the left side originally. We wanted to get to the right side, which was tan A plus cotangent B. Well, we're pretty much there. In fact, you probably could stop here, but just to be picky, I'm going to go ahead and switch these orders so it matches exactly. Of course, addition is commutative, which means you can switch the order with no problem. So this is the same as the tangent of A plus the cotangent of B, which matches exactly where we wanted to end, so we'll put our little end symbol there and be done.